In Texas, explosions rip through a refinery.
You had the black smoke rising up, but you could also just see flame, 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 flame.
A catastrophic collapse in Iowa.
It was something I will never ever forget. It was almost apocalyptic.
In Australia, a cracking miscalculation.
It became one of those things that people talk about, wondering what could have possibly gone so wrong.
And in Denmark, a bridge disaster that very nearly turned to tragedy.
There were people working on the bridge. There were people passing under the bridge. You want to know, how could this happen?
With big bills, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings, some with deadly consequences. These catastrophes are every engineer's worst nightmare. Sometimes engineers strive for style, sometimes for substance, but always for safety. Because even a small mistake can trigger a major catastrophe. Like this shocking disaster in Texas at a major oil refinery.
It looked like a scene from a disaster movie. The explosion was so strong, so massive.
Devastation on a terrifying scale.
Heavy-duty steel, just bent, missing, gone, destroyed. There was not a structure in sight.
An engineering tragedy that left a city reeling.
It was like a bomb blew off. Never saw nothing like it in my life.
Across the planet, every major economy relies on oil. And in the US, one state accounts for more than 40% of all production, Texas. Journalist T.J. Olds knows the story well.
In Texas, oil is bigger than big. It is where oil was first taken from the ground and turned into refined product. You hear a lot of times oil referred to as black gold or Texas tea. It is what makes the heart beat in the state of Texas.
To say oil is huge in Texas is a massive understatement. In a good year, it's worth more than $220 billion. That's more than the entire economy of New Zealand.
All that black gold starts life deep underground in a seething cocktail of crude oil. Before it can turn the wheels of the modern world, it has to be refined. At mammoth facilities like this 6-kilometer wide complex in Texas City on the Gulf Coast. During the late 90s, it was owned and operated by BP.
The refinery in Texas City was the third largest in the U.S., capable of refining more than 450,000 barrels of crude a day.
Mass producing millions of liters of highly explosive compounds is incredibly dangerous. Mark Holtzapfel is a professor of chemical engineering.
One way of thinking about an oil refinery is it's a bomb. Typically, the chemicals are volatile and flammable and explosive. Everybody that works there knows this, and so safety is an extremely important part of the culture.
The volatile chemicals can be turned into more than 2,000 products, and one of the most in demand is gasoline, produced in the so-called Isom Unit.
The isomerization, or Isom Unit, basically rearranges the liquid's molecular structure to create a higher grade gasoline.
The boiling heart of the Isom Unit is the 50-meter-high raffinate splitter, a distillation column where oil is heated to around 135 degrees and vaporized, breaking the raw crude into different products based on their boiling points.
The volatile parts rise to the top, and the heavy parts stay at the bottom. So based on the volatility, how easy it is to vaporize, you can separate the various components.
The components are then further refined and blended to create regular gasoline. with operations running 24/7, 365 days a year. On March 24, 2005, Assistant Fire Chief Jesse Rubio was on call at Texas City Fire Station 1.
While I was laying in my bunk, I heard what sounded like someone banging on the door. The ceiling tile moved up and down, and that's when I noticed, okay, that wasn't normal.
Journalist TJ Olds was in his office.
There was this low rumble. I went outside and saw a black plume of smoke coming up.
We got into our rescue truck and we responded to the scene.
At 1:20 p.m., a huge and violent explosion from inside the Gulf Coast refinery shook the city.
It was not anything I had ever witnessed in person before. You had the black smoke rising up, but you could also just see flame here, and it just billowed and billowed. And you could see it for miles. It looked like a scene from a movie.
The pressure from the blast triggered more violent explosions, igniting fires across the plant, engulfing an area approaching 5 acres.
They were bringing in air ambulances, helicopters to land and take people out. There were employees who had run, who had jumped over the fence in many cases, and they were along the ways here and being treated and triaged right here on site, then taken away.
It was very horrific. Injuries that we've never seen before. Heavy-duty steel, just bent, missing, gone, destroyed.
Refinery worker Brian Ambrose was at home preparing for his shift.
I was working the night shift, and my wife at the time said, "Your plant's on fire." I said, "My plant's on fire." Got to the TV and I looked. I couldn't believe it. It was the Isom. It was the unit I worked.
Brian was one of the lucky ones. Hundreds of others were on site at the time.
By the time I got there and you looked, it was like a bomb blew off. Unbelievable.
More than 40 mobile trailers used as temporary offices were damaged, 13 completely destroyed.
The explosion was so strong, so massive. Trailers that had been just destroyed and turned into sticks.
There was not a structure in sight. These were all gone.
180 workers were injured. And despite rescuers' best efforts, sadly, 15 more lost their lives.
I still feel for them people. Nobody should go through that. I'll never, ever forget what happened that day.
With more than 100 refineries across the country still working around the clock, it was crucial the cause of the blast was established.
Within 24 hours of this happening, the big question came is, how did this happen? Why did it happen? The nation, and in many ways the world, was looking at this too.
After the disaster, investigators knew that the initial explosion had come from the Isom Unit. Just before the blast, the unit was being restarted.
A restart is one of the most dangerous times because you're taking cold product and heating it up. If anything's gonna go wrong, that's when it'll go wrong.
During the restart, oil is pumped into the 50-meter tall distillation column. At its base, 2 safety gauges linked to 2 control rooms, monitoring liquid levels to prevent vapor pressure from building up.
During normal operations, there should only be around 2 meters. If the level goes even 30 centimeters too high, it activates an alarm. There's even a second gauge just above the first one to act as a failsafe.
The filling liquid did trigger the first warning, but as the level continued to rise, the top gauge, which should have acted as a failsafe, malfunctioned.
And so the crew that was starting that unit up was putting more in there thinking they had room. They didn't.
The liquid reached a height of nearly 30 meters. That's more than 15 times normal. But incredibly, the faulty gauge was telling operators that it was just over 2.5 meters and gradually falling.
The climbing liquid compressed the gases in the tower, triggering 3 emergency relief valves, which sent the hot liquid to a venting system known as the blowdown stack.
Essentially what a blowdown stack is a drum that has a pipe at the top of it. When you have an overflow of highly explosive, highly volatile product, would go into that drum and the vapors from that would be released and it would blow out from that. But when it gets overfilled, it doesn't work.
Instead of venting vapor, the blowdown stack shot nearly 30,000 litres of hot, highly flammable liquid into the air in less than 2 minutes.
It was like a geyser. Just it came out, this explosive product coming out of the top of this blowdown stack.
The equivalent of nearly a tanker truck of gasoline fell to the ground, creating a huge flammable vapor cloud.
All this vapor needed was a spark. About 7 meters away, 2 workers were in a diesel pickup with the engine running.
Any engine runs on a mixture of air and fuel. But in this case, the air itself had fuel in it. And so when that air with the fuel got into the engine just ran faster and faster and faster. Even though they tried to turn it off, it wouldn't turn off. And they ran out of the truck knowing that something bad was going to happen.
That truck revved up just based on all that explosive vapor going into it. And that ignited what became a fireball that went down on the ground, hit the unit, and then took the whole unit up with it.
Investigators now understood how the blast was triggered, but not what had caused the overflow. Attention turned to the gauge in the distillation column, which had failed to activate the alarm. For a complicated refinery, it was a remarkably simple device.
Essentially, it's the same thing in your toilet, the float that tells you what the liquid level is in your toilet. They have an industrial float, and that piece of equipment malfunctioned.
Investigators found a hole in the float, which appeared to have formed before the disaster. They concluded it had either sunk or failed to float on the surface of the liquid.
They had a false reading. They thought they had a small amount of liquid in there, and so they were basically flying blind because the instruments were not telling them the proper situation.
Following the tragedy, more detailed checklists and safety reviews were introduced, and exclusion zones were established for both unit startups and shutdowns.
The first lessons learned were getting folks away from facilities unless they really had to be there. Now, when you have a startup, everybody is told. So you know, hey, we got to clear out, let's be ultra safe on this.
All non-essential workers and temporary structures were permanently relocated away from the danger zone.
This was the largest explosion accident in American history at a refinery, so it definitely got people's attention, and we will learn from this experience.
The Isom Unit remained shut down for more than 2 years. But with lessons learned, the refinery has been operating safely for more than a decade.
It really tears me up to see when people don't go home the way they showed up to work. And I hope that a day like the Isom never happens again.
Wherever they build, engineers must always consider the elements. Underestimate Mother Nature, and the consequences can be devastating. Like this catastrophe in Iowa that brought down a vital railroad crossing.
The river forecast went from 24 feet to 28 feet, then came up onto the structure and up onto those rail cars.
A bold rescue effort that didn't pay off.
The image of the rail cars in the water, it was something I will never ever forget. It was almost apocalyptic.
And a battle with engineering that Mother Nature won.
We've learned through painful experience, forces that come to bear on structures are tremendous and frankly quite frightening.
Iowa, sprawling across the Great Plains, is the largest grower of corn in the US.
Millions of acres of Iowa farmland are dedicated to growing corn. They harvest billions of bushels a year. That's almost 20% of the national corn production.
Most of it comes here to be processed, the city of Cedar Rapids. And what better way to get it where it needs to go than by railroad? For about 100 years, the Cedar Rapids and Iowa City Railway, or CRANDIC, crossed the rapids on a bridge like this, designed for shallow, sandy rivers. Bridge engineering specialist Matt Rouse explains.
If the ground conditions are particularly favorable near the surface, which is usually a very sandy type of soil, sometimes bridge foundations are much shallower. And it so happened that the CRANDIC Bridge had relatively shallow foundations.
Built in 1903, the original nearly 250-metre-long bridge consisted of 4 steel truss spans. The bridge legs or piers stood on shallow but wide concrete foundations known as spread footings.
Many structures, and certainly bridges, use a spread footing as the foundation for the pier. And the idea is to distribute the loads from the pier to the soil, which is usually a very sandy type of soil. The slab would have a thickness similar to this block that we're standing by here. They tend to do that so that they are very rigid and can better distribute those loads to the surrounding soil.
Spread footings are great for distributing load on soft ground. They're also much simpler to build than deeper foundations, which is especially difficult in the middle of a river.
The bridge carried up to 100 trains a day without a hitch for over a century until 2008. In early June, an unprecedented flood swept through Cedar Rapids, devastating everything in its path. Susie Kettleson from the local school district was worried.
I had never seen anything like this before. It just kept coming and coming. This was a 500-year flood.
As the rains kept falling, the river kept rising. For Professor of Environmental Engineering Larry Weber, this was unparalleled.
About 1,300 blocks of the city were inundated by this event. You know, City of Cedar Rapids had to evacuate 30,000 people overnight. The damage was devastating.
With water rising to historic levels, one major concern was the CRANDIC Bridge, which was in danger of being overwhelmed.
Each day brought more rain and more bad news in the forecast. As we add rainfall, day by day by day, the river forecast went from 20 feet to 22 feet to 24 feet.
On June 10, 2008, the railroad took drastic action.
They were concerned that if the waters rose far enough that it would push the steel truss off of the large concrete piers. So they loaded several train cars with rock and put them on the bridge to try to hold the bridge down.
The river was flowing at around 4 million litres per second and rising fast.
The river forecast went from 24 feet to 28 feet, so the river then came up onto the structure and put a tremendous amount of lateral force on the bridge and the rail cars.
At 9:43 a.m. on June 12th, the CRANDIC Bridge was finally overcome by the flood. 14 loaded rail cars, 3 steel trusses, and 3 concrete piers were swept into the river.
It's unbelievable, the amount of water that basically penetrated the whole city. And then when you saw that the CRANDIC Bridge actually collapsed and the image of the rail cars in the water, it was something I will never ever forget.
In the aftermath of the disaster, the CRANDIC Railroad crossing was cut off, lying in a mass of rubble and debris.
The collapse caused major disruption. Trains were rerouted hundreds of kilometers out of their way to get into Cedar Rapids.
This was the only bridge to fail in the floods and left many wondering why had the CRANDIC crossing collapsed when others had survived.
The one big difference was the use of rail cars to weigh this bridge down. Some suggested that played a part in the collapse. But while it might sound unusual, it isn't unheard of.
The Krandic Railroad has deployed that approach before, and it worked very successfully. This event simply exceeded the forecasted flows and the forecasted height and resulted in the failure.
That's a railway bridge that is regularly loaded with train cars loaded to the top. But I would not imagine that the additional load led to the collapse.
Instead, attention turned to the pier's concrete foundations, the spread footings. It turns out they were susceptible to a relatively common phenomenon known as scour.
Scour is one of the challenges of river engineering. As the river water is flowing through the channel, it's moving sediment particles along the bed of the river. When we put a structure in the middle of the river, like a bridge pier, then water that's flowing to that structure has to accelerate to get around the structure and can move more sediment particles. And so it scours a hole on the downstream side of these structures in the middle of rivers.
Maybe just as a simple demonstration of how a bridge pier might undergo erosion or scour, set up a simple bucket of sand here, and let's let this wooden stake represent our bridge pier. And normally it's very stable, but under a high flow event, you can see this scour basin immediately forming around the base.
As the flood intensified, so did the flow around the piers, increasing the scour and weakening the foundations, compromising the integrity of the bridge.
So the fast-moving water around the base of the pier scoured out or eroded the supporting soil around the base of the spread footing, which caused the piers to tip over.
Scour is one of the most common causes of bridge collapse in the U.S. Some estimates suggest that up to 16% of all bridge failures are caused by scour.
When the 100-year-old bridge came up against the 500-year-old flood, the winner was clear.
Scour is just a very unpredictable event, and a flood the magnitude that Cedar River experienced was just beyond the range of floods that were considered at the time that that bridge was built.
After the flooding receded, every ballast car was retrieved and restored, and a new bridge constructed. This time the foundations consisted of 90-centimeter diameter shafts drilled down into the bedrock.
They did go in and fortify the foundations below the piers. Now, instead of using spread footings, we will drive steel piling in to the river and then pour the concrete cap of the pier on top of that steel piling. So even if scour happens around the steel piling, the structure of the steel maintains the integrity of the bridge.
The new bridge opened just over a year later, on July the 6th, 2009, at a cost of around $8 million. And once again, the Krandic Railroad is rolling over the river.
I think what's important for us as engineers is that when we have failures, that becomes a matter of our understanding, and that then becomes part of future engineering design.
Urban engineering isn't just about function. With landmark projects, architects strive for unique, standout designs. But one-of-a-kind projects come with big risks. Like this catastrophe in Australia that was breaking at the seams, with a giant wheel that drew everybody's eye.
The landmark was at the heart of a bustling city. It was a very public place to fail.
A design flaw that crippled an icon for years.
It became one of those things that people talk about, wondering what could have possibly gone so wrong.
Melbourne, Australia, is the nation's second largest city. With 5 million residents and growing, it's now one of the most popular destinations on the planet. Mark Murdoch is a local tourism writer.
Melbourne's a multicultural city and a very exciting place to live. And the people here are very curious for new and interesting experiences. And it's some of these qualities that make a city that's actually at the end of the world, one of the world's most livable places.
Melbourne has everything. Great weather, sports, culture. It's a big hit with tourists, and more than 10 million people a year visit the city.
In 2008, locals and tourists alike were excited by the arrival of an iconic new attraction. A $100 million observation wheel. At around 120 meters or 40 stories high, the first wheel here was the tallest of its kind in the Southern Hemisphere.
Melbourne is known for trying to bring the best of what the world has to offer to the city. And people had been watching the success of the London Eye over in the UK and had the idea to bring some of the best of that back here for what then became the Melbourne Star Observation Wheel.
When the London Eye opened in 2000, it was the first of a new generation of super tall, modern observation wheels.
The London Eye set the bar high for the rest of the world to follow, and massive observation wheels opened up everywhere from Las Vegas to Singapore.
Each has its own unique design, but the basic principles are the same. Structural engineer Santo Pascuzzi explains.
The observation wheel is very similar to a bicycle rim. So you've got an external rim supported by spokes, and the spokes are supported by a main hub, which spins around a spindle. And the spindle is supported by struts down to a foundation.
The ride might look effortless, but gravity exerts huge forces on the structure, which has to push back. As the wheel rotates, those forces push and pull it in every direction.
All the joints are subject to tension compression at different times on their cycle around the wheel. And when the spokes are positioned in the lower part of the wheel, it experiences the greatest amount of tension to hold up the whole rim of the wheel. When the spokes are at the top of the wheel, it's in less tension and more compression.
With most of the modern big wheels, your eye is drawn by the outer rim, and the hub and the spokes are just the mechanics. The Melbourne wheel is different. It has a central feature, the iconic star from the Australian flag. And that star isn't cosmetic. Those are the spokes.
Instead of steel cables, Melbourne's spokes were made from hollow steel trusses welded together to create a space frame in the pattern of a 7-pointed star.
The London Eye uses about 67 spokes, and they're much narrower cables rather than bigger structures. By having more cables, you are distributing the stresses around the supports of the rim and also at the hub, whereas using less spokes, such as the Melbourne Star, you're concentrating the loads at each spoke, so each spoke takes a bit more load than the London Eye.
There's a reason most bicycle wheels have lots of spokes. The rim is evenly supported all the way around, and all the stresses are spread. Fewer spokes can work perfectly too, but clearly each connection has to work much harder. And on the scale of a bicycle, that's no problem. But the Star weighs around 1,500 tons.
The giant iconic wheel first opened for business for the 2008 summer break during an unusually strong heatwave, even for Melbourne.
2008 was a scorcher in Melbourne with temperatures in the mid-40s in centigrade. That's around 110 in Fahrenheit.
A few weeks after the grand opening, a contractor working on the original wheel spotted a problem. Soon after, these pictures were leaked online.
The Melbourne Star was open for 40 days before a technician who was installing LED lighting noticed some worrying cracks in the wheel. In total, there were 14 of them, and some of them were as many as 3 meters long. And so safety authorities ultimately shut down the wheel at that point.
3 meters is about 10 feet. That is a long crack. And there were more than a dozen of them. In a structure almost 40 stories tall, clearly something was seriously wrong here.
With the wheel shut down, engineers made a closer inspection, hoping to get the ride operational as soon as possible.
This is a $100 million project, and as part of that, you're using some of the best engineers in the world in what's a very, very unique and interesting design problem. And I think the expectation is that if there is a problem, it can be resolved.
Rumours were running rampant as to the cause of the cracks, from poor welding to unstable foundations. Fingers were even pointed at the extreme weather.
Initially, they blamed a record heat wave during that period. So there were 3 days that were over 43 degrees, the hottest of which was over 46 degrees. And so initially, the operators blamed the heat, but in time it became clear that the issue was actually with the design rather than the unusual heat during that period.
2 months later, the owners conceded the cracks were due to a design flaw. The details weren't made public, but the location of the cracks suggested the design was unable to cope with the ever-changing forces of rotating.
I believe low cycle fatigue was the main cause of cracking in this Melbourne Star wheel. Low cycle fatigue is when the wheel experiences both tension and compression at the joints with a long period of time between each cycle. When the stresses exceed the yield strength of the steel, it reaches its plastic deformation with every cycle. With plastic deformation, cracks form, and with each cycle, the cracks will propagate into longer cracks.
A big clue in low cycle fatigue is the word low. That means the fatigue happens after only a few cycles or turns of the wheel. That's no good for a structure that has one job, to rotate.
Experts said the wheel was never at risk of collapse, but the cracks were too serious to fix.
It wasn't a great start to what was supposed to be a very iconic attraction in Melbourne. People are normally reasonably forgiving, but the problem was that that initial shutdown, which was expected to be resolved in a year, turned into 2 years and then turned into 5 years. So it became one of those things that people talk about at dinner parties and at the pub, wondering what could have possibly gone so wrong.
The radical solution was to take the wheel down and start over with a modified design.
As the project went on, it became clear that the issues are more fundamental than that, and unfortunately, the entire wheel had to be sold for scrap. They did retain the cabins and the support structure, but the rest of the wheel was gone.
With the old wheel on the scrap heap, it was clear that something had to be done differently the second time around.
The star was simplified. The connections from the spokes to the outer rim have been strengthened up via trusses. Compared to the previous design, it's a lot more sturdy.
This was a costly, very public fail, but thankfully no one was hurt. It's a reminder that in big engineering, trying something new always comes with risks.
In unique designs such as the Melbourne Star, there are always new aspects to engineering to consider. However, if you bring it back to basics and just focus on the fundamentals, you will have a greater chance of mitigating the chance of failure.
With the replacement in place, residents and visitors can enjoy the unique view from the new and improved Melbourne Star. When it comes to big engineering, every last detail must be checked and double-checked. Because sometimes it's the most basic oversights that lead to catastrophe. Like this disaster in Denmark, which exposed critical flaws in construction.
It was very dramatic, it was very bad. It was a very disturbing picture.
A catastrophic bridge collapse that very nearly turned to tragedy.
People have been standing in these areas and they had to grab the net not to fall down on the road.
Fundamental engineering errors that caused chaos on one of the country's most important highways.
There were people working on the bridge. There were people passing under the bridge. You want to know, how could this happen?
Denmark, a small nation with a long coastline that plays a vital role in European travel and trade. Local journalist Ulrik Andersen explains.
Denmark sits at the crossroads between mainland Europe and Scandinavia. Every transportation route goes through Denmark and to Sweden or to Norway.
In 1962, work began on a comprehensive highway system known as the Big H. At its heart was the E47, the first freeway in Denmark, running from the capital Copenhagen directly into Germany.
Everything depends on a well-functioning road network. It's a very important cog in the European transport network.
But this cog was becoming clogged. So in 2014, to ease congestion around the capital, the road was widened from 4 to 6 lanes, which involved more than just a new road surface. Professor of Engineering Christos Georgiakis explains.
The widening of the E47 was a very, very big project. It was, in a way, kind of not just an engineering concept, but an architectural dream. There was the idea from the architects to sort of build a boulevard through Copenhagen. People wanted the widening of the road because there was enormous amounts of traffic on the E47, a lot of time spent in vehicles, getting to work, coming home in the evening. So a lot of people welcomed this, and they understood that this disruption was going to be for the benefit of all. When you widen a road like this, you have to look at what existing infrastructure you have. Older bridges, more often than not, cannot be lengthened.
In all, 7 bridges needed completely rebuilding. The freeway was a vital thoroughfare, so the road would stay open, while concrete for the bridges would be poured above, a process known as cast in situ.
When you're casting a bridge in situ, you can put temporary supports in the locations where you're going to end up putting the permanent supports, and that allows you to open up the road below.
Wooden molds known as formwork are built in the shape of the bridge on top of temporary steel supports. Then concrete is poured into the mold, and when hardened, the deck is lowered into place.
There's a good reason for casting the bridge in one giant mould. Having joints would create potential weaknesses. But this way, when the concrete hardens, you effectively have one solid, strong structure.
The big difficulty is that, in fact, you're having to carry almost all of the dead load of the bridge by temporary formwork. So all of this concrete that you're pouring in, that is almost all of the dead load of the bridge, and it is in liquid form. And that's the most dangerous and critical part of constructing such a bridge.
Although risky, casting the bridge in situ was the best option.
This tried and true formula was common engineering practice. It allows you to build entire bridges, but still keep that all-important traffic flowing.
On September the 27th, 2014, concrete for the Eggebækvej Bridge, 16 kilometers north of Copenhagen, was about to be poured. Erik Larsen is head of construction at the Danish Road Directorate.
It was a Saturday. The casting was started early in the morning. Normally this size of bridge, the casting will take maybe 10-15 hours.
Just before 9:30 p.m., 26 workers were on the bridge pouring the western side of the deck when the whole structure rocked sideways.
The casting process was approximately 2/3 near the end when everything went wrong.
Without warning and with workers still on top, nearly 40 meters of wooden formwork collapsed.
2/3 of the mould were already full, and the concrete would take days to fully harden. Much of it was still wet and just spilled out.
Police immediately closed the road, and our people went to site immediately also.
Erik's colleague, engineer Christian Munk Petersen, was one of those who witnessed the aftermath.
It was only 5 kilometers from where I live. This was the site I saw when I arrived. Exactly what you see on this picture here. The traffic has stopped, the bridge has partly collapsed, but the steel structure was still standing.
Around 800 tons of wet, reinforced concrete had come crashing down in seconds. Professor Christos Georgiakis was working nearby.
I came out almost immediately to the bridge, A lot of the concrete had fallen down onto the road below. The reinforcement that was in had slipped out of the formwork. Some of the supports underneath, it was obvious that they had buckled. It was a very disturbing picture.
Despite buckling, the fact that the steelwork held firm may have prevented this catastrophe from turning to tragedy.
About 20 persons were up here when the accident happened, and they had to grab to the net not to fall down on the road. And actually, I spoke to a young man who has been sitting out here. Then he was thirsty and went in to get a Coca-Cola, and when he was in to get the Coke, it fell down and it saved his life. And also down on the road, there was traffic on the road, but no cars were hit by the debris, or everyone stopped before an accident happened.
Incredibly, no one was seriously hurt. But with a key transportation link shut down, people wanted to know how such a routine build could go so disastrously wrong.
We're not accustomed to these kind of accidents, so you immediately start to wonder what went wrong in this particular instance.
The E47 in and out of Copenhagen was closed and traffic rerouted, causing chaos on road and rail networks. But before they could thoroughly investigate, Danish authorities realized they faced a much more immediate and potentially deadly problem.
Because they didn't know at that point what had gone wrong, they had to put the work on similar kinds of construction where you pour the concrete in place under increased scrutiny.
After this collapse, we had at that moment 85 or something like that bridges in our pipeline to be casted. So we made an immediately stop for casting of bridges.
This is the way the Danes make most of their road bridges. They had to shut down all these projects immediately.
Early investigations into the Eggebæk Bridge disaster quickly discovered the root of the problem. It seems a vital step in the wooden formwork had been overlooked.
It was pretty obvious that the formwork of the bridge had failed. Normally what you would expect in the wooden formwork is to have some longitudinal bracing. So any kind of longitudinal movements which might occur due to the pouring of the concrete, they allow for the formwork to stay together and not kind of concertina or collapse on itself.
To do its job, formwork needs to both support the weight of the wet concrete and counteract any horizontal movement. That's normally done with what's known as longitudinal bracing.
That formwork, that bracing was not present. This lack of longitudinal bracing led to a collapse of the truss work and then the subsequent collapse of the bridge.
These trusses were not stabilized enough, so they tilted. But when they tilt, the concrete, 800 tons, falls and have a huge impact on the steel structure. And actually, this falling was measured like a small earthquake.
These miscalculations meant that the formwork was insufficiently supported, but the error wasn't detected until after the collapse.
This particular failure could have been prevented. If we had sufficient overview on the project, then this lack of the bracing between the wooden trusses would have been picked up.
Within weeks, work began on a replacement bridge with lessons learned from the collapse.
After the collapse of the bridge, the road directorate managed to get another company to come in and rebuild the bridge. The bridge was built in a similar way, cast in situ, but with a different support system.
Completed in 2016, once again this vital artery was up and running and commuters safe from potential harm.
And it went without any significant problems. So today traffic just flows on the E47 as it was supposed to all along.
The lessons learned from this disaster are a powerful reminder of the importance of coordination, communication, and double checking.